US Physics Olympiad, year 2023, USAPHO, final round. This examination had two parts, as usual, Part A and Part B. Each part had 3 questions and lasts for 90 minutes. Problem A1. Circus act. In this problem we consider a small ball bouncing back and forth between 2 points. In all parts below, the acceleration of the gravity is g. Collisions are perfectly elastic, air resistance is negligible, and the impact points are at the same height. The diagrams are not drawn to scale. Question A. Consider a ball bouncing between 2 inclined planes, which each make an angle theta less than 90 degrees to the horizontal. The ball has speed v0 at the impact points, which are separated by a distance d. Question 1. The ball can bounce back and forth along the same path, as shown. For what values of theta is this position possible? For these values, what is v0? Question 2. The ball can also take one trajectory while traveling to the right and a separate trajectory when traveling back. Let phi not equal 0 be the angle between the paths at the impact points. For what value of theta and phi is this motion possible? For these values, what is v0? Question B. Now, suppose the ball bounces within a semispherical well of radius of curvature r. As in part A2, alternates between 2 distinct points which have flight times t1 and t2 not equal t1. Find all the possible values of r in terms of t1 and t2. Question C. Finally, suppose the well has a sinusoidal shape described by y as function of x equal negative L multiplied by sine 2x over L. The ball takes 2 distinct paths with the flight times t1 and t2 not equal t1, and the horizontal distance between the impact points is less than pi L. Find all of the possible values of L in terms of t1 and t2. Solution for question A. Consider a ball bouncing between 2 inclined planes, with each make an angle theta less than 90 degrees to the horizontal. The ball has speed v0 at the impact points, which are separated by a distance d. First, the ball can bounce back and forth along the same path, as shown. For what value of theta is the motion possible? For these values, what is v0? Solution. To go back and forth on the same path, the ball must impact the plane normally, which means that theta is the angle of its velocity to the vertical. The range of the ball is v0 square over g multiplied by sine 2 theta, which implies v0 equal square root from dg over sine 2 theta. That was solution for the first question from A. Solution for the second part from question A. The ball can also take one trajectory while traveling to the right and a separate trajectory when traveling back. Let phi not equal 0 be the angle between the paths at the impact points. For what values of theta and phi is this motion possible? For these values, what is v0? Solution. The two paths have the same initial speed and the same range, which means the initial angles of the velocity to the horizontal must be pi over 4 plus or minus phi over 2. Since the initial and final angles to the normal are equal in the collision, the angle of the planes to the horizontal must be theta equal 45 degrees. Given this, phi can take any value between 0 and 90 degrees. Considering the range yields d equal this expression, or v0 square over g multiplied by cosine phi, from which we find v0 equals square root from dg over cosine phi. As expected, this reduces to the answer above as phi going to 0 and becomes infinity as phi going to 90 degrees. That was solution for question A. Solution for question B. Now suppose the ball bounces within a semispherical well of radius of curvature r. As in part A2, it alternates between two distinct paths with a flight times t1 and t2 not equal t1. Find all of the possible values of r in terms of t1 and t2. Solution. From the previous question we know that the slope of the wall is theta equal pi over 4 at the collision points. So we have distance d equal r multiplied by square root from 2. X displacement with the time t1 is v0 multiplied by cosine pi over 4 minus phi over 2 multiplied by t1, which is equal to distance r by square root from 2. Y component of velocity in the upper point is 0. So we have v0 sine pi over 4 plus phi over 2 equal g multiplied by t2 over 2. Now transforms this formula to v0 cosine pi over 4 minus phi over 2 equal g over t2 over 2 equal g t2 over 2. We can divide this formula by this formula and finally get the radius r equal g t1 t2 over 2 square root from 2. This is the only possibility for radius, and that was solution for question B. Solution for question C. Finally, suppose the well has a sinusoidal shape described by y as a function of x equal negative L sine 2x over L. The ball takes two distinct paths with the flight times t1 and t2 not equal t1, and the horizontal distance between the impact points is less than pi L. Find all of the possible values of L in terms of t1 and t2. Solution. The slope of the wall is theta equal pi over 4 at collision points. So we have in one end first derivative equal negative 1 and on other end positive 1 on symmetrical wall. In the first case we have negative 2 cosine 2x over L equal negative 1, or cosine 2x over L equal 0.5. So here we have roots like this. X equal positive or negative pi L over 6. In the second case we have this equation, which leads to roots pi L over 3 or 2 pi L over 3. So we can show it on a graph like this. So on the same level of y as a function of x, we have two pairs of solutions, this one and this one, which corresponds to two pairs of points, x1, x2 and x1, x2. First case give us d1 equal 5 pi L over 6, and the second case give us pi L over 6, which corresponds to radius r1, 2 equal d1, 2 over root 2 from question B. Using results from this question B, we have d equal g t1 t2 over 2, or finally L1 equal 3g t1 t2 over 5 pi, and L2 equal 3g t1 t2 over pi. That was solution for question C, and here we finished discussion for problem A1. US Physics Olympiad, year 2023, USAJMO, final round. Problem A2. Time is a flat circle. A particle of mass m and negative charge negative q is constrained to move in a horizontal plane. In the situations described below, this particle can either oscillate back and forth in a straight line or move in a circle. These two modes of motion are interesting because they generate linearly and circularly polarized radiation, respectively. But in this problem you may ignore any energy lost to radiation. Part A. A large positive charge big Q, much greater than small q, is fixed in place at a distance r directly below the origin of the plane. Question 1. When the particle is a distance small r much less than big R from the origin, find an approximate expression for its potential energy due to the charge big Q to second order in small r over big R up to an arbitrary constant. You may use this result for the rest of the problem. Question 2. If the particle oscillates linearly with the amplitude A much less than big R, what is its angular frequency omega L? Question 3. If the particle performs circular motion with radius small r much less than big R, what is its angular frequency omega L? Part B. Now an additional negative charge negative q is fixed in place at the origin of the plane. Question 1. What is the equilibrium distance r0 of the particle from the origin? Question 2. If the particle oscillates linearly with the amplitude A much less than r0, what is its angular frequency big omega L? Is it higher or lower than small omega L? Question 3. Now suppose the particle performs circular motion with radius r equal r0 plus delta r, where delta r much less than r0. What is its angular frequency big omega L in terms of omega c, r and delta r? Is it higher or lower than omega c? Solution for part A. A large positive charge big Q much greater than small q is fixed in place at distance big R directly below the origin of the plane. First question. When the particle is a distance small r much less than big R from the origin, find an approximate expression for its potential energy due to the charge big Q to second order in small r over big R up to an arbitrary constant. You may use this result for the rest of the problem. Solution. First, let's draw the picture. Origin is right here. Big charge Q is on a distance big R from the origin below, and the small charge negative Q is distance small r to the right from the origin. So the potential energy of the particle relative to infinity is this one, which is approximately equal this one. Here we have used the binomial theorem of the square root, since small r much less than big R. So we have this approximation for x much less than 1. This constant doesn't matter, so we could eventually write this as this one, which is exactly second order small r over big R. So that was solution for the first question from part A. Solution for the second question from part A. If the particle oscillates linearly with the amplitude A much less than big R, what is its angular frequency omega L? Solution. For the simple harmonic motion, potential energy equal 1/2 kx square if in the origin it's equal to 0 and x is displacement. In our case we have potential energy again proportional to displacement square and equal to 0 in origin. It means that if we assume that constant k equal this expression, we have the same problem as spring with the constant k and mass m. So it means that we have omega L equals square root from k over m, which is this square root. As usual, for simple harmonic motion, the amplitude does not alter the frequency. That was solution for the second question from part A. Solution for question 3, part A. If the particle performs circular motion with radius small r much less than big R, what is its angular frequency omega L? Solution. For a radially symmetric parabolic potential, circular orbit can be thought of as a simultaneous harmonic oscillation in the x direction and the y direction. Both oscillations have the same angular frequency omega L as delivered in part 1, so the answer is the same. That was solution for question 3, part A. Solution for part B. Now an additional negative charge, negative q, is fixed in place at the origin of the plane. First question. What is the equilibrium distance r0 of the particle from the origin? Solution. With the additional charge at the origin, the total potential energy of the particle as a function of r is this one. Notice that the potential energy as a function of position has a ring of minima with a certain radius r0. When the particle is not in motion, its rest position is somewhere along this ring. The value of r0 can be found from delta v over delta r equals 0, which gives us r0 equal big R multiplied by cubic root from small q over big Q. That was solution for the first question of part B. Solution for question 2 from part B. If the particle oscillates linearly with amplitude A much less than r0, what is its angular frequency, big omega L? It is higher or lower than omega small l. Solution. A linear oscillation involves the radius r oscillating around the value r0, which we calculated in previous question. Taylor expanding the expression for Vr in part B1 around r0 give us this expression. Now we can use result for V. So it means that the second derivative from V in point r0 equal this expression, which is this one. And because only this part responsible for oscillation, we have that second derivative from V. That's exactly coefficient K in model of spring constant mass oscillation. So we have big omega L equals square root from K over M, or this one, which is root 3 multiplied by omega small l. It means that big omega greater than small omega. That was solution for question 2 from part B. Solution for question 3 from part B. Now suppose the particle performs circular motion with radius r equal r0 plus delta r, where delta r is much less than r0. What is its angular frequency omega big C in terms of omega small c, r and delta r? Is it higher or lower than omega small c? Solution. For circular motion with radius little bit greater than radius of equilibrium r0, the orbit is above, but is very close to the bottom of the ring of minima r0. For such small delta r, the force linearly depends on difference r minus r0, as in Hooke's law with a constant k equal this expression, which we counted already in previous questions. Now Newton's second law gives us that this restoring force must be equal to centripetal force m omega square r0. From here we can count that this angular velocity or angular frequency of circular motion equal this expression. Notice that the orbit frequency now explicitly depends on the orbit radius through delta r. So unlike in the case of the usual harmonic oscillator, in this case one can generate circularly polarized light with a wide range of frequencies by exciting circular motion with a different radii. Since delta r much less than r0, the angular frequency big omega c much less than small omega c, so that adding the charge negative q at the origin has made the orbit much slower. Intuitively, this is because the set of potential minima is a flat circle, so that the orbit frequency can get arbitrarily small for arbitrarily small angular momenta. This is connected to Goldstone's theorem in quantum field theory, which states that spontaneously broken symmetries give rise to low frequency modes. So, finally we gave the answer for question 3 from part B, and now we finish discussion for whole problem A2. US Physics Olympiad, year 2023, USAPHO, final round. Problem A3. The motive power of ice. In the Carnot cycle, a gas is heated at a constant temperature Th and cooled at constant temperature Tc. Furthermore, no other heat transfers occur and all other steps of the cycle are reversible. The laws of thermodynamics state that any such cycle must have efficiency nu equal W over Q in, where W is work done by gas and Q in is heat input inside the cycle, which is equal to 1 minus Tc over Th. Below we will explore two other heat engines which recover this efficiency in certain limits. Part A. Consider the following heat engine involving 1 mole of ideal monatomic gas. The gas begins at temperature T0, pressure P0 and volume V0 and undergoes 4 reversible steps. First step. The gas is expanded at a constant pressure until its temperature rises to 1 plus beta multiplied by T0. Second step. The gas is expanded at constant temperature until its pressure falls to P0 over alpha. Step 3. The gas is contracted at a constant pressure until its temperature falls back to T0. Step number 4. The gas is contracted at constant temperature until its pressure rises back to P0. First question. Which steps require heat to be transferred to the gas? For each such step, give the total heat input in terms of P0, V0, alpha and beta. Second question. Under what conditions on alpha and beta would we expect the efficiency of this heat engine to approach that of a Carnot cycle, working between the same maximum and minimum temperatures? Third question. Find the efficiency of this heat engine for general alpha and beta. Solution for Part A. First question. Which steps require heat to be transferred to the gas? For each such step, give the total heat input in terms of P0, V0, alpha and beta. Solution. Obviously that heat is added to the gas in the first two steps, from this point to this point and from this point to this point. In the first step we have heating at a constant pressure, which has a molar heat capacity Cp equal 5R over 2. So from here we have Q1 equal Cp multiplied by delta T, and delta T is beta T0. Using universal gas law, we have RT0 equal P0 V0, and we have finally that Q1 equal 5 over 2 beta P0 V0. In the second step, the heat added to the gas compensates for the work done while it expands. So we have Q2 equal 1 plus beta RT0 logarithm V final over V initial. Again, RT0 equal P0 V0, and the relation V final over V initial is back proportional to a relation for pressures for constant temperature. It means that this relation is just alpha. And finally we have Q2 equal 1 plus beta multiplied by P0 V0 logarithm alpha. With the same reasoning we can count what is Q3 and Q4. Q3 will be the same as Q1 but negative, because that's equal to Cp multiplied by delta T, and delta T is negative delta T from the first process. So it means that for Q3 we have negative 5 over 2 beta P0 V0. And finally Q4 equal work done over gas with a constant temperature, which is again RT0 logarithm Vf over V initial, but now they are reversed. So it means that sign is negative here. Finally, we can count what is total work done by gas. That will be this expression, or beta P0 V0 logarithm alpha. And now we can count what is efficiency for this process. That will be work done by gas over Q in. And Q in is just Q1 plus Q2. And finally we have this expression, which is answer for question 3. But now let's compare it to efficiency for Carnot cycle. For Carnot cycle with the same high and low temperatures, we have beta over 1 plus beta. Let's compare it with the formula for our process. Here, if beta is infinitesimal, this efficiency will be almost the same as for Carnot cycle. So it means that only for beta much less than logarithm alpha, we have efficiency going to efficiency for Carnot cycle. But this happens only when beta is very small. It means that delta t is very small and going to 0. This is the only condition for which this efficiency could be compared with the efficiency for Carnot cycle. So totally this is the full solution for part A. Part B. Now consider a heat engine built around the freezing and melting of water, which occurs at a pressure-dependent temperature Tc from P. Initially, a volume of V of water is squeezed underneath a piston so that it experiences the total pressure P1, and the water is on the edge of freezing with the temperature Tc from P1. The engine then undergoes 4 reversible steps. First step, a mass is slowly placed on the piston, raising the total pressure to P2. Second step, the water is cooled to temperature Tc from P2 and frozen. Step 3, the mass is slowly removed from the piston, lowering the pressure back to P1. Step 4, the ice is heated back to temperature Tc from P1 and melted. Assume that water and ice are incompressible with the fixed densities ρ W and ρ C. First question. What is the net work done by this engine in terms of P1, P2, V and the densities? Second question. Assume the latent heat per unit mass L to melt ice is large, so that freezing and melting account for essentially all of the heat transfer in the cycle. What is the efficiency of the engine in terms of P1, P2, L and the densities? Third question. Since we assumed all heat transfer occurs during melting or freezing, this cycle has the same efficiency as the Carnot cycle in the limit where P1 and P2 are very close. Use this fact to enter an expression for delta Tc over delta P in terms of Tc, L and the densities. Solution for part B. Question 1. What is the net work done by this engine in terms of P1, P2, V and the densities? Solution. The system expands at the pressure P2 and contracts at the pressure P1. So the net work done is pressure difference, which is P2 minus P1, multiplied by delta V. So that's process 2 and 4. So using expressions for delta V through V, ρ W and ρ I, we can get this expression for work. That was solution for the first question from part B. Question 2. Assume the latent heat per unit mass L to melt ice is large, so that freezing and melting account for essentially all of the heat transfer in the cycle. What is the efficiency of the engine in terms of P1, P2, L and the densities? Solution. We know that efficiency equal work done during this process, which we counted in the first question, divided by Q in. The heat transferred in is used to melt the ice. So we have Q in equal raw water multiplied by volume V and multiplied by latent heat L, and the work done by process was counted before. That was this one. So finally efficiency equal to this expression, which is a solution for question 2, part B. Question 3 from part B. Since we assumed all heat transfer occurs during melting or freezing, this cycle has the same efficiency as a Carnot cycle. In the limit where P1 and the P2 are very close, use this fact to infer an expression for delta T over delta P in terms of Tc, L, and the densities. Solution. The Carnot efficiency for the same high and low temperature is this one. T high minus T low divided by T high. Efficiency for Carnot cycle equal to this expression, where TCP1 is high temperature and TCP2 is low temperature. For our process we have efficiency which we counted in question 2. Now equalizing this we have these equalities. Now combining we can write this expression, and for P1 going to P2 we have as a limit first derivative from temperature by pressure equal this expression. This was solution for question 3 part B, and here we finished discussion for problem A3. US Physics Olympiad year 2023 USAPHO final round. Problem B1. Electric roulette. Consider a cylindrical solenoid with radius small r, length L much greater than small r, and n turns per unit length. It is made of one continuous wire, with the top connecting back to the bottom as shown at left. In the middle of the solenoid, part of the wire is replaced with the assembly shown at right. A uniform conducting rod of mass m and radius r is connected to the bottom half of the solenoid, and is free to rotate about the solenoid's axis of symmetry. The end of the rod slides on a fixed conducting ring, which is attached to the top half of the solenoid. This assembly and the solenoid form one continuous conductor carrying total current I. First part. What is the inductance of this system? Assume that n r much greater than 1, so that the magnetic field produced by the current in the rod and the ring is negligible. Part B. When the rod is within a uniform vertical magnetic field B, find the torque it experiences in terms of I, B, and R. Part C. If the rod rotates with the angular velocity omega, the electrons inside have a tangential velocity. Find the electromotive force across the rod in terms of omega, B, and R. Now we will consider the dynamics of this system in some simple situations. For all the parts below, neglect energy losses due to friction, resistance, and radiation. Part D. First, suppose the system initially carries no current, and the entire system is inside a uniform external magnetic field B0, parallel to the axis of the solenoid. If the rod is given a small initial angular velocity, its angular velocity will oscillate in time. Find the period of these oscillations. Part E. Next, suppose there is no external magnetic field B0 equals 0 and at time t equals 0 the system carries current I0 and the rod has 0 angular velocity. First question. The rod's angular velocity omega as function of time approaches a value omega 0 after a long time. What is omega 0? Second question. Find omega t over omega 0 in terms of omega 0, t, n, and l. You may use the integrals on the reference sheet. Solution for problem B1. Part A. What is the inductance of this system? Assume n r much greater than 1, so that the magnetic field produced by the current in the rod and the ring is negligible. Solution. Magnetic field of solenoid, which is mu0 n I. So the flux through one turn of the solenoid is mu0 n I multiplied by cross-section area, which is pi r square. We have total n multiplied by l turns in total, so it means that total flux will be F1 multiplied by number of turns, which is nl. And finally, inductance is flux over current, which is mu0 n square pi r square l. That was solution for part A. Part B. When the rod is within a uniform vertical magnetic field B, find the torque it experienced in terms of I, B, and R. Solution. The torque is due to the Lorentz force on the current as it travels radially outward from the center of the disk towards its edge. If we take a small part of this rod on a distance s from center and length delta s, that will be delta tau equal negative delta f multiplied by s, which is negative bi delta s multiplied by s. Now we can integrate this result from 0 to r, which will give us total torque, which is negative 1/2 bi r square. The minus sign indicates that the torque tends to slow down the rotation when I is defined in the direction shown in the figure. This is consistent with the defining positive angular velocity and the torque by the right-hand rule. If you define it the other way around, this equation and the several others below would pick up sign flip. Since we didn't specify the sign convention in the problem text, either set of signs received full credit. That was solution for part B. Part C. If the rod rotates with the angular velocity omega, the electrons inside have a tangential velocity. Find the electromotive force across the rod in terms of omega, B, and R. Solution. By Faraday's law of electromagnetic induction, the electromotive force around a closed path is equal to the negative of the time rate of change of the magnetic flux is equal to the negative of the time rate of change of the magnetic flux enclosed by the path. In our case, magnetic field is constant, so we have to use formula EMF equal negative delta F over delta T, which is equal to negative B multiplied by delta A over delta T, where delta A is area of the small triangle which created by angle delta theta. So we have delta A equal 1/2 r squared delta theta, and finally EMF equal negative 1/2 omega B r squared. That was solution for part C. Next, now we will consider the dynamics of this system in some simple situations. For all the parts below, neglect energy losses due to friction, resistance, and radiation. Part D. First, suppose the system initially carries no current and the entire system is inside a uniform external magnetic field B0 parallel to the axis of the solenoid. If the rod is given a small initial angular velocity, its angular velocity will oscillate in time. Find the period of these oscillations. Solution. Here we can use results which we got in previous parts. Rotational motion of our rod, we have 1/3 mr square multiplied by delta omega over delta t, which is angular acceleration, equal torque applied to this rod. We remember that torque was 1/2 B0 I r square. Due to Kirchhoff's loop rule, we have EMF minus inductance L multiplied by delta I over delta t equals 0. Using expression for EMF, we have EMF equal negative 1/2 omega b r square. It means that di over dt equal EMF over inductance L, which is after all this expression. From first two, we have delta omega over delta t equal 3 over 2 b0 over m I. And now we can take a first derivative by time from this expression, and using expression for delta I over delta t, we have second derivative by time from omega equal this expression or this expression. And finally we can see that second derivative from omega proportional to omega with a negative sign. This is exactly equation for simple harmonic motion, and from here we can find what is the period of oscillation of this omega. That will be period equal this one. That was solution for part D. Part E. Next, suppose there is no external magnetic field B0 equals 0 and at time t equals 0, the system carries a current I0 and the rod has 0 angular velocity. First question. The rod's angular velocity omega as function of t approaches a value omega 0 after a long time. What is omega 0? Solution. Now, because external magnetic field is 0, we have to use magnetic field created by current I, which initially I0. That will be in solenoid mu0 n I. From a previous section we found that angular acceleration, which is delta omega over delta t, equal negative 3 over 2 b over m I. So using this expression for magnetic field B, we can write that because I square is positive, we have angular acceleration is always negative, and angular velocity will be increasing in negative direction and reach the final omega 0. From other hand, we had delta I over delta t equal 1 over 2 pi omega b square L. Now, using this expression for B, we got that delta I over delta t equal omega I divided by 2 pi and L. That because omega always negative, we have delta I over delta t is negative and the current always decreasing. Because we are not losing any energy, we have energy conservation. And because now we see that there are no oscillations, so it means that total energy equal mechanical energy for rotation plus energy of a magnetic field inside of the solenoid. and we have in any time this expression. And because final current is 0, we have this equation. Now we can divide our expression for energy conservation by right part. We will get equation equivalent to energy conservation. Omega square over omega 0 square plus I square over I 0 square equal 1. Here we can use expression for inductivity. Inductivity for solenoid was mu 0 n square pi r square L. Now using this expression and this expression we can find what is omega 0. Omega 0 will be this expression, which is a solution for question 1 part E. Question 2. Find omega t over omega 0 in terms of omega 0, t and L. Solution for question 2. Now we can use our energy conservation in this form. Also, we found that delta omega over delta t equal this expression through I square. So now we can use I square over I 0 square in this form and put it to this expression, which will give us this one or this one. This is a typical differential equation. So this is the solution for differential equation, and finally we can express it in form of omega as a function of t over omega 0 equal hyperbolic tangent from negative omega 0 t over 2 pi ln. That was solution for question 2 part E, and here we finished discussion for problem B1. US Physics Olympiad, year 2023, USAPHO, final round. Problem B2. Fast and Furious. A space program wants to accelerate a spaceship to final mass m equal 100 kilograms to relativistic speeds to observe distant stars. They have two proposals to evaluate. Part A. Their first proposal is to use traditional rocket propulsion. A rocket of initial mass m0 and the final mass m that expels propellant with exhaust speed u relative to the rocket will reach a speed v equal u multiplied by logarithm m0 over m. Suppose the desired final speed is vf equal 3c over 5. In the subparts below, neglect relativistic effects and give your answers in the form 10 power n, where n has at least two significant figures. Question 1. If the rocket has exhaust speed u equal 3.5 km per second, what must its starting mass be in kilograms? Question 2. If the propellant is exhausted at rate 7.0 kg per second, how long does the acceleration take in centuries? Question 3. If the energy density of the fuel is 2.0 multiplied by 10 power 7 joules per kilogram, how much total energy is required in joules? For the rest of this problem, you should account for special relativity. Part B. Another option is to use a spaceship with a constant mass m propelled by light produced by lasers on Earth, with a total power P equal 6 multiplied by 10 power 12 watt. The light evenly impacts a sail on the spaceship and reflects off the sail directly back towards the Earth. Neglecting the orbital motion of the Earth and give all your answers in the frame of the Earth. Question 1. What is the force on the spaceship when the spaceship has speed v? Question 2. How long will it take to accelerate the spaceship to speed vf equal 3c over 5 in seconds? You may use the integrals on the reference sheet. Question 3. At the moment the spaceship reaches this speed, how much total energy has been used to power the lasers in joules? The following results from relativity may be helpful. First, the Lorentz factor is defined as a gamma equal 1 over square root from 1 minus v square over c square. Second, an object of mass m and the velocity v has momentum p equal gamma mv and energy E equal gamma mc square. The force is defined by F equal delta P over delta T. Third, the momentum and energy of light are related by E equal PC. Fourth, in the frame S prime with the velocity V multiplied by coord x relative to frame S, the energy and momentum are E prime equal gamma multiplied by E minus V px and the px prime equal gamma multiplied by px minus VE over c square. Solution for part A. Question 1. If the rocket has exhaust speed u equal 3.5 km per second, what must its starting mass be in kilograms? Solution. We can use this expression for final speed to express m0 through other parameters. So that will be m0 equal final mass m multiplied by exponent power v final over u exhaust, which is equal 100 kg multiplied by exponent power 2.2 multiplied by 10 power 4, which is approximately 10 power 22,337 kilograms. So that's answer for question 1. Question 2. If the propellant is exhausted at rate 7.0 kilograms per second, how long does the acceleration take in centuries? Solution. So here we can use formula time equal mass difference, which is m0 minus m, divided by exhaust rate, which is 7 kilograms per second. So finally that will be this expression, or 10 power 22,336 seconds, or 10 power 22,327 centuries. That was answer for question 2. Question 3. If the energy density of the fuel is 2.0 multiplied by 10 power 7 joules per kilogram, how much total energy is required in joules? Solution. Here we can use equation mass difference multiplied by energy density of the fuel, which finally give us 10 power 22,344 joules. That's the answer for question 3. So we finished with the part A. Solution for part B. Another option is to use a spaceship with a constant mass m, propelled by light produced by lasers on Earth, with a total power P equals 6 by 10 power 12 watt. The light evenly impacts a sail on the spaceship and reflects off the sail directly backward the Earth, neglecting the orbital motion of the Earth, and give all your answers in the frame of the Earth. Question 1. What is the force on the spaceship when the spaceship has speed v? This problem could be solved by different approaches. First approach, we can use Earth frame of reference during all the problem. Suppose that we have part of momentum which reached the spaceship is delta p plus for time delta t. This is not the same as momentum which was produced by lasers for the same time, because not all the light reached the spaceship for the same time. Suppose that at the same time it was reflected another momentum of light which is delta p minus in opposite direction. If we summarize these two momentums, we will get total change of momentum for our spaceship. Total momentum for spaceship was P equal mv over square root from 1 minus v square over c square. So total change of momentum for our ship was delta p, which is equal delta p over delta v multiplied by delta v, which is derivative from this part by speed v, which is this expression, and that must be equal to change of momentum for our beam light. So we have this expression. Now let's check what happened to the same portion of energy for this beam light. So we have energy from the light beam which fell on the ship was delta E plus, which equal C delta P plus, and the energy of the beam which was rebounded was delta E minus, which is equal C delta P minus. Kinetic energy for our ship was mc square over square root from 1 minus v square over c square. It means that a change of energy was a delta E over delta V multiplied by delta V, which is this expression. And this change of energy equal energy difference between delta E plus and delta E minus. So using these two expressions for change of energies, we can express them through momentum difference, which is this one. Now we have delta P plus plus delta P minus and delta P plus minus delta P minus. So we can add these two equations to eliminate delta P minus, which we don't need. So we got delta P plus equal this expression. Now we can express delta P plus through our power of our beam. So we have momentum which reached our ship was delta P plus, which is equal energy which was reached by this beam over C, but energy equal power which reached our ship multiplied by delta T. Power P plus just equal part of power which reached our spaceship. That was power multiplied by 1 minus V over C. And the delta P plus over delta T equals this expression. Now let's write expression for the force. By definition, force equal delta P of our ship over delta T, which is this expression, and using expression for delta P over delta T, which is this one, we can rewrite force in this form, and the delta P plus over delta T equal this one, and finally force equal 2 powers over C multiplied by 1 minus beta over 1 plus beta, where beta is a regular expression for V over C. That was solution for the first question in part B. Second solution for the first question from part B. What is the force on the spaceship when the spaceship has speed V? Now let's do this problem in the spaceship frame of reference. First, take beta equal V over C, where V is the speed of our spaceship. Let's take a portion of momentum delta P plus, which affect our ship over time delta T. In the frame of reference of our spaceship, this momentum became equal delta P plus prime, gamma multiplied by 1 minus beta multiplied by our original momentum delta P plus, and this is according to formula of relativity. In the frame of reference of our spaceship, which is not moving, this momentum reflects with the same quantity and the opposite sign. So that will be delta P negative prime equal opposite delta P positive prime. And now go back to our Earth frame of reference. Again, this momentum became delta P negative equal this one. And now, to count what is the total change of momentum for our spaceship, we have to use formula negative delta P minus positive delta P, which is equal to over 1 plus beta multiplied by our original momentum delta P plus. Now let's use expression for our power P. Original momentum produced by lasers was P over C multiplied by delta T, but our spaceship used only 1 minus beta part of this power, so of this energy, because the spaceship moving with the speed V and we cannot use full power. So we have delta P plus equal original power P over C multiplied by 1 minus beta multiplied by delta T. And finally we have force F equal delta P over delta T, which is equal to 2 powers P over C multiplied by 1 minus beta over 1 plus beta. This is exactly the same answer as in the first solution, which was much longer. Third solution for question number 1 of part B. In the Earth's frame, if the photons in the incident beam have a frequency Fi, then they are reflected with the frequency Ff equal this expression, where we apply the relativistic Doppler shift formula twice, since the photons are first absorbed by the moving rocket and then re-emitted by it with the same frequency. Applying conservation of momentum and using the fact that the momentum of a photon is related to its energy by E equal hf, which is equal pc, we have force F equal delta P over delta T, which is equal to delta N over delta T multiplied by H over C and multiplied by frequency initial plus frequency final, which is equal this expression. Here we have delta N over delta T is the rate at which photons collide with the sail. It is related to the rate at which photons are emitted from the source of Earth by formula 1 minus beta multiplied by delta N emitted over delta T. Finally, since the power of the laser is rate of emission multiplied by energy of photon, which is hf initial, we have force F equal 2 pi over c multiplied by 1 minus beta over 1 plus beta. which is the same answer as for the first two solutions. Question 2 from part B. How long will it take to accelerate the spaceship to speed v final equal 3/5c in seconds? You may use the integrals on the reference sheet. Solution. From previous question we found that force equals this expression. But from other hand we have delta p of our ship is this expression, which finally mc multiplied by delta beta over 1 minus beta square in power 3/2. Now we can equalize these two expressions and have this differential equation where we can split variables. So we have this equation which we can integrate and find what is the solution. So we have that total time equal this integral, and from the table given in the additional spread reference sheet we have this integral equal this expression, and when we put limits we have 5/3. So finally time equal 5/3 mc square over 2p, and that will be 2.25 multiplied by 10 power 6 seconds. So that's the total time, and that was solution for question 2. Question 3 from part B. At the moment the spaceship reached this speed, how much total energy has been used to power the lasers in joules? From previous question number 2 we found that total time equal 5/6 mc square over power p. So it means the total energy used to power the lasers were 5/6 mc square, or 7.5 multiplied by 10 power 18 joules. That was solution for question 3 from part B, and here we finish discussion for problem B2. US Physics Olympiad year 2023 USAPHO final round. Problem B3. Starry messengers. In 1987, light from supernova SN1987A was detected by telescopes on Earth. The supernova occurred in the Large Magellanic Cloud, a distance d equal 1.5 by 10 power 21 meters away, making it the closest in centuries. Observations of this event tell us a remarkable amount about elementary particles. Part A. Both light and neutrinos were produced in the core of the supernova. Neutrinos are elementary particles which interact extremely weakly with the ordinary matter. Detectors on Earth saw a few dozen of these neutrinos in a burst which occurs about t equal 3 hours before the light arrived. Question 1. One explanation of these observations is that the neutrino's speed v was faster than the speed of light c, violating special relativity. If this is the case, find v minus c in meters per second. Question 2. Another explanation is that the light was slowed down by the gas in the solar system, while the neutrinos always moved at speed c. Suppose the solar system has a uniform index of refraction n within a radius d equal 10 power 13 meters. What would n have to be to explain the time delay? Neither of these explanations seems plausible. Modern accepted explanation is that the light was trapped for some time inside the supernova while the neutrinos were able to leave immediately. Therefore, for the rest of this problem, you should assume special relativity holds. The results listed on the previous page may be helpful. The neutrinos did not all arrive at once. The first arrived with an energy of about E1 equal 40 megaelectron-volt, and the last arrived about T equal 10 seconds later with an energy of about E2 equal 20 megaelectron-volt. Part B. One explanation of these observations is that neutrinos have a small mass m, so that when they have energy E much greater than mc square, their speed v is slightly slower than the speed of light. Question 1. Find an approximate expression for c minus v to leading non-trivial order in mc square over E. Question 2. Using the information above, numerically estimate the neutrino mass m in units of electron volt per c square. Part C. Another explanation is that the neutrinos did not travel in straight lines, but rather were deflected by the intergalactic magnetic field. Suppose this field is uniform, B equal 10 power negative 13 Tesla and directed perpendicular to the line joining Earth and the supernova, and that neutrinos have charge Q equal epsilon E. Question 1. If the neutrino has momentum P, then in the presence of the magnetic field, it travels in a circle of radius r equal P over QB, which is much greater than d, and its path to the Earth has a total length L. Find an approximate expression for L minus d to leading non-trivial order in d over r. Question 2. Using the information above and assuming the neutrino mass is very small, so that the effect in part B is negligible, numerically estimate epsilon. Solution for part A. Both light and the neutrinos were produced in the core of the supernova. Neutrinos are elementary particles which interact extremely weakly with the ordinary matter. Detectors on Earth saw a few dozen of these neutrinos in a burst which occurred about t equal 3 hours before the light arrived. First question. One explanation of these observations is that the neutrino's speed v was faster than the speed of light c, violating special relativity. If this is the case, find v minus c in meters per second. Solution. If the light took a time t to arrive at Earth, then distance d equal speed of light c multiplied by time to travel, or equal to speed of neutrinos multiplied by time to travel for neutrinos, which is t small minus t big. From here we can write that v over d equal 1 over small t minus big T, c over d equal 1 over small t, and small t equal d over c. So from here we can write what is the speed difference. That will be distance d multiplied by 1 over small t minus big T, minus 1 over t, which after a little approximation give us big T multiplied by c square over distance d. And after putting numbers we finally have about 0.65 meters per second. That was a solution for the first question of part A. Question 2. Another explanation is that light was slowed down by the gas in the solar system, while the neutrinos always moved at speed c. Suppose the solar system has a uniform index of refraction n within a radius d equal 10 power 13 meters. What would n have to be to explain the time delay? Solution. The time delay t is n minus 1 multiplied by radius d over speed of light c. And after calculations we have index of refraction equal tc over d plus 1, and after putting numbers we have about 1.3, and this is such a big number that is implausible. So that was solution for second question of part A. Solution for part B. One explanation of this observation is that neutrinos have a small mass m, so that when they have energy E much greater than mc square, their speed v is slightly slower than the speed of light. First question. Find an approximate expression for c minus v to leading non-trivial order in mc square over E. Solution. Here we can use a regular expression for energy in relativity. Energy equal mc square over square root from 1 minus v square over c square. We can rewrite it in form of m square c power 6 over e square equal c square minus v square, and the last one approximately equal 2c multiplied by c minus v, because v very close to c, and from here we can find that c minus v approximately equal m square c power 5 over 2e square. That was solution for the first question in part B. Question 2 from part B. Using the information above, numerically estimate the neutrino mass m in units of electron volt per c square. Solution. From part A we found that for velocities very close to speed of light we have c minus v approximately equal t c square over d. So it means that if we compare two neutrinos with a time difference delta t equal 10 seconds, we have v1 minus v2 equal delta t multiplied by c square over d. And after putting numbers we have velocity difference is 6 by 10 power negative 4 meters per second. From other hand we have c minus v equal approximately this expression. It means that for two different neutrinos we have v1 minus v2 equal this minus this, and using numbers for E2 and E1 we have a 3 over 2 this one. Now putting expression for V1 and V2 we have mass equal 46 electron volt per c square. That was solution for question 2 from part B. Solution for part C. Another explanation is that neutrinos did not travel in straight lines, but rather were deflected by the intergalactic magnetic field. Suppose this field is uniform and B equal 10 power negative 13 Tesla and directed perpendicular to the line joining Earth and the supernova, and that neutrinos have charge Q equal epsilon E. Question 1. If a neutrino has momentum E, then the presence of the magnetic field, it travels in a circle of radius r equal P over QB, which is much greater than d, and its path to the Earth has a total length L. Find an approximate expression for L minus d to leading non-trivial order in d over r. Solution. We are computing the difference between the arc length of the small arc and the distance connecting the endpoints. If the arc length is L, the angle subtended is theta equal L over r. The distance connecting the endpoints is 2r multiplied by sine L over 2r. Then Taylor expanding for small x, sine x approximately equal x minus x cubed over 6. So we have L minus d approximately equal this expression, L cubed over 24 r square. That was solution for question 1 from part C. Question 2. Using the information above and assuming the neutrino mass is very small, so that the effect in part B is negligible, numerically estimate epsilon. Solution. The radius of path is P over QB, which is equal energy E over QBC. Substantiating expressions for L1 and L2 for different neutrinos, we have this expression for length difference. And finally we will get this expression for length difference. From here we can count what is charge Q. So because length difference equal to C multiplied by delta T, we finally have this expression, and after putting numbers we have charge equal 3.6 multiplied by 10 power negative 15 charge of electron. So from here we have epsilon equal approximately 3.6 multiplied by 10 power negative 15. Since the effects of neutrino mass and the charge add, and we know neutrinos have mass, a result yields a very strong upper bound on the possible charge of a neutrino, which as far as we know could be exactly 0. That was solution for question 2 part C, and here we finished discussion for problem B3.